Well, I think we can start. Thanks, Marten.
Thank you. Is the microphone working? Yeah.
Yeah, it's on.
Thank you. Thank you for giving me this opportunity to talk about my work. I'll be talking about some work I did using Numerical Conformal Bootstrap, and about one paper together with Slava, David, Benoit, Ning, and Balt, and further work by me. So the title of the talk is Navigating Outer Space. So why did I call this? This is not some technical term. In the Bootstrap, we have for a long time been thinking in terms of nautical terms. We talk about an island, we talk about archipelagos and a peninsula, and this all makes a lot of sense when you're searching a two-dimensional parameter space. But technology is advancing, and as technology is advancing, we are ready to lift off into outer space or hyperspace. We're ready to search for tiny little planets in the vast universe that's out there in large dimensional parameter spaces, up to 13 dimensions. So how do we do that? We use technology that we developed in this work called the Navigator Bootstrap that enables us to no, but maybe here, this one? I guess it's people joining? No, I don't know. So I will talk about this new technology that we developed in order to search parameter spaces much more efficiently, and what you need to take into account and how you have to do this when you try to obtain bounds in high-dimensional parameter spaces, and then talk about how specifically we apply this to obtain rigorous bounds on new rigorous bounds on many operators in the 3D icing model. I will compare this with another non-rigorous method that exists to obtain bounds, to attain estimates of a large part of a CFT spectrum, and I will verify whether these non-rigorous estimates are accurate by obtaining rigorous bounds on the same quantities. And I will discuss some new sparseness assumptions that you can consider when you have access to these. You have these tools that you can consider assumptions that require that involve many parameters. So before I explain this, let's start at the beginning and look what do we do in the traditional numerical bootstrap. So what you do is you test an assumption parameterized by numbers P. So for example, you've probably seen this plot of the icing kink, where you ask, if you take two sigma operators, is there some maximum allowed gap before there's an other operator exchanged? And the answer is that using numerical bootstrap, you can indeed find that this is the case. There is a region that is disallowed, and there's a region that is allowed. Is consistent with the crossing equations, and there's a region that's not consistent with the crossing equations. Now, how do you obtain such a bound? Well, we can phrase this question of whether something is allowed or not by search for a linear functional, but what it means is that traditionally what you do is you take some point and you just check whether it can be excluded. You might check this point and you find it can be excluded, might check another point, find it is allowed, and like this you might bisect towards finding this bound. And like this, you can do this for all points, and then you have this figure. Now, the next step of what was done, what you can do, is you can consider a mixed set of correlator, and you can look for a theory that only has one relevant Z2 even and one relevant Z2 odd operator. In this case, you start looking for a tiny island. Now, how do you find this tiny island? Well, you can still do some grid and hope that it is dense enough to hit it, or if it's not, you keep adding points, and at some point, you find it. And this is still a fine method to do it when you're looking at this two-dimensional space. But as you keep adding dimensions, this is getting tougher and tougher. These islands, you might have known, heard, can be very tiny. And if you look for a tiny island in a large dimensional space, you're going to need a very big and dense grid. So you basically need n to the, let's say, curly p points where this is the dimensionality of the search space. So it scales exponentially, and that means that it's prohibitive. It means that usually in numerical conformal bootstrap, when you try to obtain rigorous bounds, it's limited to a handful of parameters, in problems involving only a handful of parameters. So what would you prefer to have? It would be better if you want to search this island and you check some points, you wouldn't just get an answer of allowed or disallowed, but it would tell you, well, you're roughly this far and you should move in that direction. And then maybe you overshoot and you say, well, now it's there. And then you find it very quickly. So what we need is some function that guides us. So it would be nice if you could have some function that you, and if the answer here is not just allowed or disallowed, but it tells you, well, you're this high, this far off from, let's say, the zero line that is the island, and it tells you to in what direction to move. So so what properties would we like such a function to have? Well, firstly, it should be able to tell apart just what the previous allowed, disallowed answer already told us. It should just tell us how to tell apart allowed and disallowed points. So for example, it should be positive for disallowed points, and it should be negative or 0 for allowed points. And okay, 0 at the boundary by continuity, which runs ahead a bit, but we would like it to be continuous. And even better, ideally we can do this thing where I say that we can easily compute the direction in which we have to move, not just know roughly how far we are away from it. So ideally we want it to be differentiable. We also want it to exist everywhere and to be bounded. You could try a very naive approach to this function and might run into the problem that the answer is it runs off to infinity everywhere except in the island. And then this function is not useful for telling you where to go. So it should be, at the very least, bounded from above. And then ideally it would be cheap to compute. If it costs a lot more, orders of magnitude more to get this information of a direction than to get this allowed, disallowed, it might not be worth it. And ideally it is cheap to compute using the standard technology that is used in the field. And finally, it would be nice if you could also very cheaply compute this gradient that I mentioned, where you want to know how does this function change under a small perturbation. So also cheap derivatives. So bounded from above is more important because I say that it's positive in the disallowed region. So the most important part is that when you are in this disallowed region, you get an idea of how to go to the allowed region. So if it's a function that, let's say, does this and then it does this, and I want to check a point here and I want to see where it moves, then if this is infinite just from now on, then that doesn't really tell me any information. Now you can ask, can it be arbitrarily go down? Well, at the very least, if that's the case, then you've already found the island, the negative point. But also we will see in the construction, you can also see that sort of understand when it should not be not be bounded from below. But this is less of an issue whether it's bounded from below. The question is whether it's differential close to the kink? Right. So we can get into differentiability. So just by inspection, we found, at least in the case of some simple navigator function for the 3D icing model in the work 1, that it is, and I mean this is just by inspection, by plotting it and by looking how it looks everywhere, investigating this, that it is once differentiable. There is actually a special line where it's not twice differentiable, and this can be a slight issue, but it's not prohibitive. It doesn't mean that you can't effectively use this anymore. But yeah, I was planning to say, well, basically this a bit later. Right. Right, that's true. There's multiple, we constructed multiple formulations of navigator functions, and you can always pick one that is bounded also from below. So how do we construct such a function? Again, we will look at the basics of the conformal bootstrap. So we are solving equations of this form, where we have some known piece that corresponds to the identity, and then we have some sum over operators that we allow to appear in this sum, and which operators we sum over, which operators we allow, that depends on our assumptions. For example, we might assume that there's only one relevant operator, which means that in this sum, only one such a term can appear. And let's call this C for crossing. And so depending on this value, these assumptions, I write down the assumptions with S, and P parameterizes these assumptions. There either is a solution or there is not a solution. And so, for example, we saw that in this region X, there is no solution, whereas in that other region, there might be a solution. And, well, let me still. So depending on SP, this either does or does not have a solution. Now say we modify this equation. we add an extra term. Okay. I call this modified crossing. Now say that we can construct a function m such that modified crossing has a solution with some for some lambda equals lambda 0 greater than 0. If this is the case, no, that's not good. Then we can define a function to be the minimum value of lambda such that MC has a solution. And we'll see that these are basic properties that we want. So first, by construction, for the moment by assumption, there exists such an m, such a function, that there's a solution to this equation with this value lambda 0. Which means that the function is immediately bounded from above. I should include here such that for all p, for all assumptions that we make, the whole search space, there exists a solution with value lambda 0. This guarantees that our function is bounded from above because the minimum value is at most this value lambda 0. No. Sorry, 1 second. M depends on P. There is always such a function. What is your question? Yes, I mean, it's true. There is also always such a function. I'm going to say that there is and say which one, an example of one that there is. Sorry, you're saying that if you leave MUV free, then there's always an MUV you can pick to guarantee this. Yes. Perhaps it will be slightly more clear once I tell you also what an example of such an MUV is. So we saw that it was bounded by lambda 0, and for any p satisfying the original crossing equation, which we call allowed, would go allowed, there is a solution to MC with lambda 0 equals 0, right? Because that's just, if you set lambda to 0, then that's just the original equation. Now it's also easy to show that if a solution exists with for both lambda 1 and lambda 2, then by taking a convex positive combination of the equations, you can easily show that there exists a solution for any lambda in the interval in between. And so from this we can also see that if the navigator, here I should have said that the fact that for any p satisfying the original crossing there's a solution to modified crossing with 0, this immediately gives us this property that the minimum has to be 0 or lower. So we already find that in the allowed region it is negative. We would also like to know that only in the allowed region it is negative. That is, that it's positive in the disallowed region. And you can show this by looking at what happens if NP is smaller than 0 somewhere. Well, that means that there are two solutions. There's a solution with namely the one with lambda equals 0, lambda equals lambda minus this number that is either negative or 0, and also lambda equals lambda not. And so it follows that any number in between is a solution. So specifically, lambda equals 0 is a solution. And so we find that this value p is allowed. So we find that navigator function is negative only for allowed points and is positive for disallowed points. Now, okay, I promised you such an M can be constructed, but we're physicists, so you shouldn't trust me, and you should, I should show it to you. So let me keep that. So to understand this, let's just look, when does this not have a solution, this equation, the original crossing equation? Why would it not have a solution? So in principle, for any consistency conditions for correlators that you study, there's always a solution to this equation, as long as you, if for example your assumptions are only that the operators that appear have to be above the unitarity bound, that it has to be unitary CFT. Because in this case there's always the generalized free field theory. But in numerical bootstrap we don't want to study the generalized free theory. We already know it and we want to study interesting theories. So what we always do is we exclude it somehow by our assumptions. Now, guaranteeing that there's a solution to the modified crossing equation is just a simple matter of taking the terms that the GFF terms that we don't allow to appear here and putting them here. So we can take MUV to just be the sum over the GFF operators that are missing in the other sum by our assumptions of these functions weighted by the known OPE coefficients. And now we have a solution to this with lambda. This gives a solution with lambda equals 1. And so we have a function that's bounded by 1. And now we can see two things. One is that, well, we can gain an intuition for what it is that we do by minimizing this lambda. We're basically starting off, for any point there is this solution of the GFF, but what we're interested in is a solution with lambda is equals 0, so we're trying to minimize away from the boring solution towards the interesting one. And what you can also see, so we've seen that these properties hold, we've seen that it's bounded, and to see whether it's cheap to compute and whether it's can be computed using standard technology, that should now, for people with experience with numerical form bootstrap, be clear, because the task of minimizing this lambda is just the task of minimizing the OP coefficient of a known isolated term, which is just a standard optimization task that we can compute using STPP. So in fact, we have a computation to minimize this, which is exactly a standard STPP task, which can be is therefore cheap to compute and can be computed using the standard technology. It is because it's an optimization task, we know that this is slightly more expensive than checking whether something is allowed or disallowed, but this is only like a factor of 3, and we will see that we more than gain this back by having this function to guide us. So about the other properties, I already said, so this we can't show from first principles, but by inspection, just it seems to work well. It seems that it is continuous, it is at least differentiable once everywhere. There might be some special regions where it's not twice differentiable, and yeah, it's interesting to see what the meaning of that is, but it's not a major obstacle to what we want to do. So what, and, oh yeah, finally, I will, in the interest of time, I will skip going into the details on the cheap derivatives, but because the problem that we're solving to minimize this lambda is a semi-definite program where we, in order to find this, you have to be at an extremal solution, and you have to basically the fact that you're at extremality implies certain conditions on your semi-definite program, and because of this, you can show that if you have computed lambda, the minimal lambda for some value n, for n of p, then you can compute the change and their small variation for free by only computing the input, the change in the input, and you don't need to run STPP again. You don't need to run the optimization again. So we also have this property that the gradient is cheap to compute. So if we have all this, maybe I should have, okay, no, start it. What can we do now? So one thing that we can do I already discussed. We can find a tiny island by walking directly towards it. And we can do this by minimizing this navigator function, which we do with the quasi-Newton algorithm. And once we have this island, what do we want? Allowed point. We find some allowed point here. What do we want to do next? Well, we want to compute some bounds on, yes.
So, based on the construction of this function, based on the construction of m, you start from a disallowed point, let's say. The minimum lambda has value 1. Is that correct? For all disallowed points?
So if you ask very roughly what the function looks like, it might very roughly be something like this, with here 1. Is this, and here, for example, in the island 0, and then this is the island.
So what changes when we get closer to an island? We are just subtracting away we are just putting back the rest of the GFF terms, right?
Right, so your minimum, so there is no solution to the crossing equations at some point under your assumption. But there, as you get close to the island, there is like almost one that if you just add in some contribution from the GFF operators, then at least to these truncated crossing, there's one detail I skip in the numerical conformal bootstrap. You search for a functional, so you don't solve the full crossing equations. In effect, you project down to a subspace, and in this subspace you can have solutions with finitely many operators, and basically close to the Ising in this, there will be a solution, for perhaps not the full Ising solution, but there will be a solution if you add in a little bit of this, the missing GFF operators.
So if you start really far, then the gradient is basically 0, so it's not telling you.
So it's not, it keeps telling you something. It's not quite 0, and yeah, so there are some issues with whether you start in the convex, whether it's convex where you start. We found some small trick where instead of optimizing the navigator directly, you do some transformation on it that increases the domain of convexity, where it's convex slightly. So there are also some small tricks like this. But in general, as long as you start, so for example in Ising and in other cases that I've seen, if you start somewhat close to the island, then there should be like proper attraction to the island. Right. This is of course an obvious worry, especially if there are positive local minima, because and you don't reach the one that you're looking for. So this would be a problem. Again, so what could you do? What could you do to, if you wanted to avoid such a problem, one thing you can try, I mean, then it becomes a global optimization problem, and these are just hard. But like a very naive thing that you can do, which we tried, is that you basically start 20 different points. And in this case, you see if you start 20 different points from different areas, you might hope that if you pick the right point, you go into the other minima. And what we find is if you start 20 different points, that they all go to the same minimum. But this is, yeah, you can't show this from first principles. And in different cases where you apply the navigator function, there might be, it might look differently. In my experience, it has not been problematic in such a way, but yeah, it could be. But yeah, even then you can, you would start wondering also whether there might be meaning to when this happens. Is there like something that would be a valid CFT if your assumptions slightly changed? You can start thinking of this kind of questions. So in practice, here I don't find it at all. I've heard that of someone where there's a case where it's, I think, more understandable also why it happens, where it can happen. And it's because there's two close by CFTs and one is only slightly excluded. And I've heard someone that can be the case. Also, very naively, just if we look at the Ising plot, we of course know that there in a sense are multiple, in this case, we always draw this island, but then there is also this peninsula. And so clearly the navigator has to like go between that and become negative again there. But this in general, if you test it, the navigator does actually run off like to arbitrary negative values as you go to infinite external dimensions. And this, basically you can see that this has to do with a known observation that as you go to larger and larger external dimensions, your bounds usually get weaker and weaker.
There's one example of the near vacuums that's appeared in the 3D numerical bootstrap. So for the new bounding things, it's possible that there could be two near vacuums. And then I guess it would be interesting to use the navigator function to check if there are two local minimum near the plane.
No, I did not, but I agree. That's where you, yeah. So, yes, sorry. So you want to find the tiny island, and you also want to, well, let me read in 2D just because that's then my drawing capabilities are not amazing. The other thing you want to do, okay, previously people tried to use like grid and triangulation searches to get the shape of the island, but what you really want to know is where the extremities are, so that you can put a bounding box, and so that in your table you can say, well, delta 1 equals 0.5123 with some rigorous error bar. Here. So to do this, you can again do this more efficiently by using optimization techniques. And in this case, you have just a constraint optimization problem where you try to extremize in certain direction under constraints that you have to stay within the island, within n smaller equal than 0. And so you can do this, and you can find these extremities. And again, similar to what you asked, you can wonder, what if the shape is like this? You report your error bars, and now, oops, you missed the fact that there was this shape. And basically, again, you can't exclude this. If this is the case, you could also have worried with the previous methods that maybe a grid could also miss it. But now you actually have better shot of at least finding these things, because what we do is we, again, extremize from multiple points. So you might go from all of these, and so you have a good chance of also detecting such a fit shape. Then, so for 2- and 3-dimensional things that I'm plotting here, this already gives a cute speed up. It's nice. But really, where it is revolutionary is in high-dimensional spaces, because the fact that you always just have the direction in which you have to move and an idea of how far you have to move means that you're much less sensitive to the dimensionality of the search space than this grid searches that grow exponentially. So for large dimensional spaces, it really is a game changer. And so there are many applications. I can name a few. So one thing is just there are these large bootstrap setups that have a lot of power that can solve problems like stability of the Heisenberg magnet, or that can bootstrap Grosnevier-Yukawa. And these involve many parameters. And similarly, there are spinning bootstraps of the bootstrap of spinning operators. And these involve many parameters, and they're numerically heavy, so you really need to be efficient with your computer time. And for this, like, it opens, many new things are possible now. You can consider mixed correlator systems of many more operators. And it really removes a bottleneck. Similarly, you can study families of CFTs. So add as your parameters of your search space, for example, some number n corresponding to the global symmetry group, such as ON or ON cross O2, which is specifically Slava mentioned, we're working on with some people in Paris. You can also consider the space-time dimension as one of the parameters and look for a family of CFTs at different dimensions. And in fact, Stefanos will talk about this, I think, a bit later, about some work where me, him, and Johan Henriksen followed the 4 minus epsilon expansion between from 4 down to 3 and a little bit beyond, because there's an interesting effect called level repulsion happening just around there. But in this talk, I will just be talking about how I used it to determine a larger part of the Ising spectrum. So one thing you might think about, so now we can bound more than a handful of parameters because we can, well, why? Let's first make it clear why. So normally we ask, for example, the problem that there's only one relevant singlet. And so we would be scanning over this delta epsilon, and we would find some rigorous error bars. Now what I'll be doing is saying, let's go look a bit higher and consider that there's only two operators below 6. So we assume that there's only two operators below 6. This assumption can be, is based on, for example, epsilon expansion, also based on some results that we will be comparing against and testing against from extreme functional method. And finally, you can also now make it even more rigorous, better motivated by the fact that you can study in the 4 minus epsilon expansion what happens with these operators and follow them all the way down. And you see that there's this continuous family of solutions where, again, this is way above, it's 6.8, it's way above 6. And also, it doesn't matter, I should say that it doesn't matter too much. You can take this 5.5 or 6.5. Results won't change much. So under this assumption, you can now bound this extra delta epsilon prime. You can also bound all the upper E coefficients related to it. Well. And you can do the same for other sectors. You can do C2 odd. Yes?
When you say bound, you're just checking many specific values, right? So it's really, it's a grid, correct? So you're taking many specific values, delta epsilon, delta epsilon prime, and you're saying if those values are allowed, and then presumably the region is disallowed, but it's not rigorously a bound because there could always be some tiny value which would still be allowed or disallowed.
So you're using this optimization and you're looking for where the derivative just vanishes. So you're looking for these points. So you do some optimization, you find these points. Now, as you're saying, it could be that you had this, and then you might miss it. Or in this case, actually, I would find it because I run multiple points, and I would restart from these edges. But there could be something that is sharp, you don't have access to it, and you miss it. And that's true, but this would have been worse in like triangulation methods, because here, at least, here all you need to do is a point that starts like in the right region of attraction, right? So that when you optimize, it can end up in the extremity. And previously, you would really have to hit this point. You would have had to be in this spike. And also, there's a reason why we don't expect these kind of spikes to really be there. There's the behavior of how the bounds, or in this case, you can also say the navigator changes as lambda, and in general, it's just not what we find, these kind of weird spikes. Sorry, I was thinking that you were asking about, once you found an allowed point, you want to find extremities connected to it, but you're also right that you want to find the multiple islands. As it was discussed here, you want to, if there is some structure where there's two islands, you of course want to find them both. And again, so one way to do it, what we did, is that you, again, it's global optimization, you could miss it. But one thing you do is you do, for example, 10 runs, and you see that they all end up in the same minimum.
I believe your results. I'm just saying that it's not literally rigorous.
No, but it's rigorous. Let's say it's rigorous in the sense that this 3D Ising model is rigorous.
Even the 3D Ising model is not really rigorous because you're doing a grid at the end of the day. It's like, two directions are rigorous, but the other two directions are not rigorous because they're coding these tiny values.
Yes, there could be some very tiny weird spike in principle. But, well, I think there's reason to not believe that. So one is indeed like, this is a function, you can also consider this as a family of functions, as a function of the derivative order, the dimensionality of the search space for a linear functional. And you know, it gets weirder and weirder if your problem, and also you could ask this, like, is it like pi? Like, if you hit the CFD exactly, you find it. If it's any small error, you just don't see it at all. You could worry about this for the numerical conformal bootstrap. But in the end, there is actually some approximation. You're running things on a computer, and yeah, I think it would just be really weird if in this, especially in this truncated, smaller part of the crossing equation, if there was no solution in exact, you hit it right on the nose.
I mean, sorry. The point is that now they are all on equal footing, the same as delta epsilon, delta sigma determination. It's everything on the same footing. It's not as something is more precise than, or more rigorous than something else. So if you believe delta epsilon and delta sigma, you should believe everything else.
I believe it. I'm just saying it's not literally rigorous.
Well, okay. Well, you can make it more rigorous at the cost of relaxing a little bit the bounds.
Sorry, you wanted to bound which operators, and what would you want to conclude? Yeah, I think the answer is yes. You're asking, yeah, so if you do this, yeah, you find an island in like a large dimensional parameter space. Is that just the question? Yes. Yes. So in fact, so here, if you consider this, then depending on which operators you include, you can have like 4 to 8 parameters or something. But if I will show that you can do the same in other sectors. Also, I did it also in spin 2, where you have the stress tensor, and then one operator. And you can also consider all of these at once. So the biggest that I've considered is considering all these sectors at once, looking for the sparsest CFT with C2 symmetry. So one that has, in all these sectors, only 2 operators below 6. And then you find a 13-dimensional island, effectively, because you're finding all the extremities of this 13-dimensional shape. Right.
So using this new method of, say, putting a gap to 100 and then, say, like, scanning over, like, the 200 operators below 100, does that allow you to get higher twist operators? So, like, is it more precise, this thing of putting a gap and scanning over operators than just looking at the spectrum?
Yeah, let me... I think that indeed I can get back to this when I present the results. I would say if you want a very quick answer, I think slightly is the answer. But yeah, but now I've given away. No, but okay, yes.
I have one as well.
Yes.
If the shape of the island is non-convex, like a potato like this, for example, could the extremization get stuck for one of the directions? Because you go inside the island and then you extremize along the directions to get the bounds. But could this get stuck in a non-convex island?
I mean, yeah, I think there could be shapes in principle where I would not detect any non-convexity and I would make the wrong conclusion. I mean, indeed. So I do a certain things like extremizing in different directions from different extremities in order to try to find whether there ever is such like a weird shape. And I never find that that two different extremities end up in a different point. Always everything goes like, everything goes there, everything goes there, everything goes there. But it's definitely true that there could be weird enough shapes. Yeah, so one thing you can try to, if you want to keep being sure that you don't do this, then a good thing maybe to try is to do things incrementally in two ways. Do things incrementally in the number of parameters that there are, and do things incrementally in the derivative order, because yeah, you are more sure to not miss a shape if you start in like a weird shape if you start in a smaller space, and then you know that those bounds are rigorous, and you can go further and see how much it changes to see whether. Yeah, I mean might still be some art to. I think that I'm confident that the bounds hold, but yeah, there could be weird shapes. Hmm? You can walk around, exactly. So another thing you do is you can walk around. This gets you lose a little bit of the advantage if you do this in a large parameter space to walk around a very large dimensional object. But you're right, you can do this. Yeah, I agree. You lose a lot if you want. Yeah, exactly. No, I agree. I agree. You lose a lot. That's true.
If I take a big dimensional island and if I project it down to the lower dimensional, this delta sigma delta epsilon, is the two-dimensional island now smaller than the old two-dimensional island?
Yes. Sorry. I mean, it depends on which parameters you do. They might matter or not in shrinking the island, but in general, yes. So for example, the simplest example of what you do with three examples is that you would have delta epsilon and delta sigma, and you would add the OPE angle between the operators, and the island shrinks a bit. This was well known, yeah. And so exactly. So one question that you want to ask, that I wanted to ask, is if you impose this sparseness in all these sectors at once, will this do a lot to reduce the size of the island, also in the delta sigma and delta epsilon space? Yeah, so also, just to point out, some of these things are actually interesting. So we already saw in Anna's lectures this corrections to scaling, which is given basically by this value, which controls, for example, in Monte Carlo, you would have the susceptibility go as 2 minus epsilon A0 plus A1 lambda minus omega. Sorry. And so, in fact, I determined this, the first rigorous bounds on this quantity. Do I want to say that? So also, okay, one thing I should say is, so this is the new way how you can obtain rigorous bounds on more operators. But indeed, we should compare to what was already possible. So it was not possible to study this many operators rigorously, obtain rigorous bound. What was possible is to use something called the extremal functional method, which in a very simple, short way, basically, once you have some allowed point, this extremal functional method gives you an example of a solution to this truncated crossing negation. And you can try to say, well, if I take a lot of points and I sample a lot of them, maybe I get a good estimate of what can happen to these solutions, how much can they vary. And so I will be comparing a work by David Simmons Duffin, where he obtained a very large part of the CFT spectrum, the low-lying operators, and exactly by doing this, by sampling many points and looking how much they vary, he gave both an estimate of the central value and of how much this can vary. But of course, these error bars are non-rigorous. You don't know that the sampling, you're just sampling a finite number of points from some infinite dimensional space. You don't know that this is representative of the true solution. And so this is a very popular and very strong, useful technique. So it's important to check it now that we can check it rigorously. And so that's in fact what I'm doing by obtaining all these rigorous bounds. I think, so I'm guessing that I'm out of time. Yes, let me switch to the slides. They will be there? Or, yeah. Okay, then that means that I can quickly still write one thing, which I think is easier to write on the board. So for example, I find these bounds. Where this is rigorous. And you can compare this, for example, with omega as extracted from lattice simulations by Hazenboek. And so we see that we agree, so you have to subtract phi, and we add a few, I add a few digits of precision. And you can also compare with what David found. So here it's non-rigorous, but what you see is that it's very accurate. Both the central value and the estimate of the error are very rigorous. And I should say, for the technical, that this was at lambda 43, this was at lambda equals 31. And if you look at how this converges as you increase lambda, it seems to be going to basically roughly the same number and same bounds. So it seems that the extremely functional method is very accurate, and that the estimate of this error under sampling is actually also quite accurate. So I'm just showing some results in a final slide. Sorry, I have to share screen. Where is that? Oh, oops. Yeah. Okay, so these are some bounds obtained, of which the first four were already known, but the other ones are all new rigorous bounds. There were either no rigorous bounds, or in some cases, like CT, there was only a rigorous lower bound. And in general, these all match what David found in, like, they're all around his bounds, and it seems in general that, especially for operator dimensions, the extremal functional method is really accurate. There is some slight issue for OP coefficients, which might be good to highlight. Oh, is there something weird? Why is there chat? Oh, okay. There's no chat that I see. Oh, it's on this. But here the mouse is not working. Sorry, do you know what? Okay. Okay. Let's just ignore it. Okay. Sorry? We should probably finish up. Okay. Okay. So yeah, then I will very quickly say. Okay, there is something that might worry you, that I found rigorous bounds at the lower derivative order that excluded some interval of that was found by sampling by David. And normally, an example of a solution is still example at some derivative order is clearly also an example of a solution at any lower derivative order. So this might get you worried. And here's a specific point that I reran that's even further out to find that indeed there is such a solution. But there's also a simple solution to why this happens. It's because David only demands that there is only one relevant operator below 3, while I am demanding that there's 2 below 6. And so this is a known effect that in the extremal functional methods there can be spurious operators, especially there's often an operator that really isn't there, that's just at whatever gap you imposed. And effectively that means that if you have an operator here and he also finds the true one that I also find, then these OP coefficients get like the fake operator takes a bit of the real one. This was known as the sharing effect. And I just want to point out that this is consistent because you can see exactly in the solution that this is what happens. And this also shows you that the solution to get around this sharing effect and to get an accurate determination of the OP coefficients, this is the Navigator method explicitly scanning over it is a really good solution for this. And so you can actually get stronger bounds at a much lower derivative order because you exclude this sharing effect. So this was very shortly what I've said and what you asked me about, that what if you impose sparseness on all these sectors? Does it also get much smaller in delta sigma and delta epsilon? And the answer is that it gets a little bit smaller, but it doesn't seem to be that big an effect, and it might not be the best way in order to get small bounds, but it does something. And I think that it's, oh, okay, final word. So I claim that it scales much better. So I just show here some of the tasks that they did and how many points are required in order to, in blue here, find a allowed point in the island. In yellow, find the minimum of this island, and on the right, find the extremities in a task such as this, where you have to find this. And you can just roughly see that it goes roughly linear. And that was my point here. So thank you very much.
Thanks. Any other question? Well, we have an hour until the next talk, so if there are other questions, I think we can answer.
In your construction of the Navigator function, the generalized tree field contributions play a critical role. Is that just a useful trick, or was it essential?
So it's a useful trick, because there's another construction which I think is a bit less intuitive, but you can also show it works, where instead you take this sum, I erased it, you take MUV to be minus some sum over just a lot of operators, and here it doesn't matter. Here you don't have to have some physical sense, it's just enough so that well, certain orthogonality works out so that you can always add arbitrary positive number of positive operators to offset this large negative one. It's some math to show it, but this is sort of a more agnostic way where you just use math basically to show that you also get a bounded navigator function. And in fact, this navigator function looks very similar. We could ask what is the shape of the different functions. We didn't explore too fully, but in our initial explanation, it seems that if you do this agnostic approach, you basically get a very similar looking function.
I mean, is there some criterion which makes one navigator function better than another?
I think that you could say that it would be better to have something more smooth. So one problem when the navigator function gets a bit more difficult is that you sometimes have that you have a bit of this. Not quite like up, but the more you have like just the sharper racing surfaces, and the less it's just well approximated, the less well approximated it is by a quadratic function, the more difficult it is to work with. Ideally, you would have just the quadratic function going to the minimum, and then you would do one iteration of your Newton method, and you would find the minimum.
Yep, last question.
Okay, thanks.
Okay, so you spend most of the time to discuss about to apply the Navigator function to study the island. Now let's go back to the kink. So I have a question that if we use the extrema function now method to check what happens near the kink, then there's a characteristic property of this kink, which is the decoupling of the operator in the extrema spectrum, right? So my question is, in the Navigator function, can you find a similar characteristic property of the kink?
Okay, I think we can ask Marten again. We can thank Marten again, sorry.